Okay, let's get started. So at the end of last class, we were talking about composition of functions. So given two functions, f and g, f composed with g is just shorthand notation for f with g of x inside. And we saw that that's the same as taking a number we called x and sticking it into the g function. And what comes out is g of x. And then putting that into the f function. What comes out is f of g of x, or f composed with g of x. So let's take a look at an example or two. So let's say f of x equals x squared plus 3x plus 2. And let's say that g of x equals sine x. Just as an example. So let's compute both f composed with g of x and also g composed with f of x. So f composed with g of x, that's really just f with g in brackets. Oops. And you can replace either the f or the g first. I'm going to go ahead and replace the g first. So I'm going to replace g by what it actually is. So this is just f of sine x. Now we have to figure out what f of sine x is. Well, f of x, oh, wait till you're done writing. F of x is x squared plus 3x plus 2. So let me do some scratch work over here. F of r would be r squared plus 3r plus 2. Basically, whatever goes in here goes where the x is. So f of box would be box squared plus 3 times box plus 2. So f of sine x, this time sine x is your box. It's what was over here. So this is sine x all squared plus 3 times sine x plus 2. And I suppose if you want to write this as sine squared x plus 3 sine x plus 2, that would be great also. But this is perfectly acceptable. So you just replace the inside part by what it really is and the outside part with what it really is. Now let's do g composed with f of x. So g composed with f of x is really g with f of x inside parentheses. And again, I'll replace the inside first. I'll replace f first. So that's just g with x squared plus 3x plus 2. That's all f really is. Now, g of x is sine x, g of q would be sine q, g of box would be sine box. So g of this is just sine of all this. And we have two very different functions here. This function and that function. Those are very different. And you certainly can't split this up as sine x squared plus sine 3x plus 2. We know that's not how sine addition works. Are there any questions with composing functions? We can take two functions, add, subtract, multiply, divide, or compose them. Is that okay? Okay, let's move back to where we were talking about inverse functions. So recall, say f and g are inverses. We write g equals f inverse. We saw this last time. If f composed with g of x is x and g composed with f of x is also x, if the composition in either direction just gives you back x. In other words, f and g undo one another. F and G are reverses of each other. F and F inverse, we call G F inverse, are just reverses of one another. So let's take a look at some examples. Let's say f of x is x plus 2. F is just the function which takes a number and adds 2 to it. How do you undo that? How do you undo adding 2?
Subtract 2.
Subtract 2, right. So f inverse is going to be x minus 2. And we can check that these two functions are, in fact, inverses. If I take f composed with f inverse of x, that's equal to f with f inverse in parentheses. F inverse is just, f inverse is just x minus 2. And f of something just adds 2 to it, so that's x minus 2 plus 2. But the minus 2 and the plus 2 cancel out. That's just x the way it's supposed to be. And if I do it in the other order, f inverse composed with f of x, this is just f inverse with f of x in parentheses. So we have big parentheses, and then f of x is inside. This is just equal to f inverse of f, which is x plus 2. And f inverse just subtracts 2 from something, so that's equal to x plus 2 minus 2. And again, the plus 2 and the minus 2 cancel out, and they give you just plain old x, which you're supposed to get. So the opposite of adding 2 to something is subtracting 2. So if f inverse is x plus 2, then if f is x plus 2, then f inverse is x minus 2. Let's take a look at another example. How about f of x is 3x? F is the function that takes a number and multiplies it by 3. How do you undo that?
Divide by 3.
Right, you divide by 3. So f inverse is going to be x divided by 3, or we could just easily write that as 1/3 x. Dividing by 3 is the same as multiplying by 1/3. And again, you can check that that this function and this function are inverses. If you compose them in either direction, you get one. It's a little bit harder if I ask you to find the inverse of, let's say, f of x equals 3x plus 2. Here's a function which takes a number, multiplies it by 3, and adds 2 to it. Let me show you the method for finding the inverse of this function. So step 1, write y equals whatever f of x is. Step 2, switch x and y. So wherever you see an x, put a y. Wherever you see a y, put an x. Step 3, solve for y. Let's get y all by itself. So 3y equals x minus 2. Y equals x minus 2 divided by 3. So step 3 is solve for y. And step 4 is write F inverse. So where you have a y, put an F inverse. So there we go. So let me remind you that not all functions have inverses. Not all functions have inverses. And to decide which ones do and which ones don't, we need a definition. Function f is said to be one-to-one that's what I'm defining here, one-to-one if let me write this as x1, x2. So if we have two different x values, if x1 doesn't equal x2, then f of x1 does not equal f of x2. So different x values give you different y values. Remember, the y value is just f of whatever the x value is. Different x values always give you different y values, then the function is said to be one-to-one. For instance, f of x equals x squared is not one-to-one. It's not one-to-one. I can plug two different x values in there and get exactly the same thing. So f of minus 3 is 9, and f of 3 is 9. So as soon as you can find two different x values that give you the same y value, it's not one-to-one. And so we have the following, technically, theorem. I'm just going to call it a fact. Well, actually, before I get there, let me just make one more mention of something. You can tell if a function is one-to-one from its graph by using the horizontal line test. Horizontal line test. So a graph passes the horizontal line test if any horizontal line crosses the curve at most once.
What does it say by the definition when it says a function
Everybody?
f? Yeah. What does it say but in the first line of the definition for
Hang on for just a second. Let me just, I can barely hear you for some reason. Can you say that again?
yeah, what does it say like in the beginning line of the definition? Like it says said to no the top one. The top one? Yeah. It says said to and then what does it say after?
Said to be one-to-one.
Okay, thank you.
Sure. So graph passes the horizontal line test if any horizontal line crosses the graph at most one time. So for instance, f of x equals x squared is not one-to-one. Because if you take a look at its graph, the graph that you know well, it's totally possible to draw a horizontal line which crosses the curve more than once. Let's say I draw that horizontal line at height 9. Doesn't really matter where I draw it, as long as it's above the x-axis, so that is at x equals 3 and x equals minus 3. These two different x values give the same y value, so that horizontal line crosses more than once. So saying that there's a horizontal line which crosses the curve more than once is the same as saying that there's two different x values that give you the same y value. It's two different ways of saying exactly the same thing. And according to this, that means that f of x equals x squared has no inverse. I'm looking at your faces right now. If you're saying to yourself, wait a second, I can undo x squared. I can just take the square root. The square root of x is not the inverse of x squared. Let's see why. So if I take g of x equals the square root of x, which you'd think would undo the square root, then if I take a number, let's say I take f composed with g of x. So according to f and g, according to the composition here, this is just f with g of x in parentheses. And so this is f of the square root of x, because that's what g is. And if f of something is, you take it and square it, so that's just the square root of x squared. And I totally agree that that gives you x. I completely agree that that gives you x. But let's do it the other way around. It has to equal x both ways. G composed with f of x is really g f of x in parentheses. And I'll replace x by f by what it really is. So that's just g of x squared. And g takes something and takes its square root. That's the square root of x squared If I take a number and square it, and then take the square root, do I always get back to the original number? No, definitely not. It's totally possible to take a number and square it and take the square root and not get back to the original number. For instance, well, you could probably think of an example yourself. Any negative number will do. If I take the number -2 and square that, that gives me 4. If I take the square root of 4, I end up with 2, not the original number, not -2. By the way, this symbol right here means positive square root. That's why when you write out the quadratic formula, you have to put the plus or minus in front of it. So this is not equal to x. It is if x is positive or 0, but not if x is negative. In fact, this is just a fancy way of writing the absolute value of x. So it's not x. It's not necessarily the original number. So g of x equals the square root of x is not the inverse of f of x equals x squared. In fact, f of x equals x squared has no inverse. Graphs of f and f inverse are just reflections of one another. Over the line y equals x. You remember when we computed f inverse, we just switched the role of y and x. So graphically, what you're doing is just reflecting over the line y equals x. So for instance, let's say my original function is x cubed. Here's the line, of course, y equals x. Line going up to 45 degrees. By the way, you can see x cubed, unlike x squared, does pass the horizontal line test. Any line, any horizontal line crosses that curve at most one time. So if we're going to take the inverse of x cubed, which you might guess is the cube root of x, and it is, we're going to take the inverse of this. You just take this whole curve and flip it over the line y equals x. So just imagine y equals x as a mirror and flip the curve, take its mirror image over that line. So it looks a lot like this. So here's y equals f inverse of x, which you might have correctly guessed is the cube root of x. They're just mirror images of one another. And now we can see what goes wrong with x squared. From a graphical standpoint. If I try to reflect this over the line y equals x, use y equals x as a mirror, what I'm going to end up with is something that looks like this. A parabola on its side. Why is that no good for an inverse? What's wrong with this thing? Parabola on its side. It fails something that you know.
The horizontal line test.
Well, this one passes the horizontal line test, but it fails the vertical line test. It's not even a function. Remember that if a graph, if you can draw a vertical line which crosses the curve more than once, it fails the vertical line test, and it's not even a function. So this parabola on its side isn't even a function. You can draw a vertical line across the curve more than once, it means it's not a function. So this thing is not even a function. It fails the vertical line test. Vertical line test will tell you whether a graph represents a function or not. The original curve, y equals x squared, it fails the horizontal line test, and reflected over the line y equals x. What you get fails the vertical line test. Okay. That's enough of composition. I want to talk a little bit about piecewise defined functions. I think I'm going to do this by example. Let's say f of x equals, how about x squared if x is greater than or equal to 0, and minus x if x is less than 0. This is just another way of sticking two functions together. Let me draw you the graph y equals x squared. I know you know exactly what it looks like. And I'll also draw you the graph y equals minus x. Y equals minus x is a line going downhill at 45 degrees. In other words, the line going through the origin with slope minus 1. All this says, this complicated notation says, I'm going to take the part of this graph to the right of 0. So I'm going to take, if I'm graphing y equals f of x, as I've defined it up here, I'm going to take the part of x squared to the right of 0. So to the right of 0, this looks exactly like the parabola. And to the left of 0, I'm going to take a piece of the curve minus x. So I'm taking this part of this curve, and I'm taking this part of this curve. So for every x value, I've got it covered. So it's a straight line over here and a parabola over there. That's all this notation means. Take a piece of this curve, stick it together with a piece of another curve. They don't have to meet up. This one happens to be a nice continuous curve. I can draw this without picking up my chalk from the paper. That doesn't have to be the case. So for instance, if I have the curve, let's say x plus 2, if x is less than or equal to, let me say less than 1, and is equal to x, if x is greater than 1, So let me just dot in these two lines for a second. This is not the curve. I'm just going to dot in some reference lines. So y equals x, we know is the line going uphill at 45 degrees, passing through the origin. That's not the curve. I'm just dotting it in because I'm using a piece of it. And y equals x plus 2 is a line that goes uphill at 45 degrees with slope 1, but crosses the y-axis at 2 units. And that's not the curve. I'm just dotting it in because I would need it. And I have a break, something going on at x equals, oh, hang on, let me make this greater than or equal to 1. Sorry about that. Greater than or equal to 1 in that second line. So here's x equals 1, that vertical line, x equals 1. So I just have some reference lines on my page. And this says, I'm going to take this curve, I'm going to take the part of this curve to the left of 1. So I'm going to take this dotted line to the left of 1. That's going to be my curve. And to the right of 1, I'm going to take the line y equals x. And at 1, I'm in the second line. I'm right here. Now I'm not up here. At 1, x greater than or equal to 1, I'm right down here. So I'm going to put a closed circle here and an open circle here to indicate that at x equals 1, I'm actually at the closed circle, not the open circle. So here's my graph now. It just goes do, 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 and then it jumps, and then it keeps going. Perfectly nice function. It passes the vertical line test. This vertical line that I dotted in only crosses the curve once, just there. It doesn't go through the curve at all right there, because there's an open circle. So that's what this piecewise defined business is all about. Okay. I want to talk a little bit about polynomials. A polynomial function is any function that can be written in the form a number times x to a power, whole number power, plus another number, x to the next lowest power, and so on. All the way down to a constant term. For example, let's say f of x equals x cubed minus 3x squared plus 5x plus 2. Or g of x equals x minus 1 times x plus 3. That doesn't look like this, but you could make it look like this. You could make it look like this by boiling this all out. X times x is x squared plus 3x minus x plus 2x minus 1 times plus 3 is minus 3. Now it looks like that. So these two are exactly the same function, so they're both polynomials because they're the same. Or h of x equals x squared. Just because it's missing some terms doesn't mean I can't write them in. I could write this as x squared plus 0x plus 0. So any function you can write like this is a polynomial. The largest power of x is called a degree. And low number degrees have special names. And just so you understand what I'm saying this semester, I'm going to give you some of the names. So let's say the degree, make a little chart here. Name. The degree 0 polynomial is called a constant. So how about f of x equals 3. Largest power of x there is x to the 0. It's just a constant polynomial horizontal line. Degree 1 polynomials are called linear. This is straight lines. The degree 2 polynomials are called quadratic. For instance, x squared plus 2x minus 3. Degree 3 polynomials are called cubic. For instance, x cubed minus 3x squared plus 5x plus 2. Degree 4 are called quartic. Degree 5 are called quintic. If you want, they don't come up very often. I won't use that word very often, but just in case. Quartic and quintic, if the handwriting isn't clear. After that, people just say 6th degree polynomial, 7th degree polynomial. But they do use these words quite a lot. Graphs of polynomials have no breaks and are smooth. Graphs of polynomials have no breaks and they're smooth. So for instance, nice and smooth, no sharp turns like, you know, for absolute value of x that has a sharp turn, so shaped like a V. These points where you stop going down and start going up, or start going up and start going down, in your pre-calculus class, you might have called these turnarounds. We're going to have another name for them this semester. I'll just call them turnarounds for now. An nth degree polynomial has at most n minus 1 turnarounds. So a third degree polynomial has at most 2 turnarounds. A cubic polynomial not all of them have exactly 2. Let me show you 2 cubic polynomials. Y equals x cubed minus 3x has exactly 2. 1, 2. Y equals x cubed plus 3x has none. It looks like this. It has no terminals. You know that y equals x to the a 4th degree polynomial, has only 1 turnaround, not 3. This is shaped just like a parabola. Well, not exactly like a parabola, but just same general shape. This has only 1 turnaround. But there are 4th degree polynomials that are shaped like W's with 3 turnarounds. The ends of polynomials, like you see how this end goes down and this end goes up and this end goes up and this end goes down? Odd degree polynomials have ends that go in opposite direction. So one goes down, one goes up. Even degree polynomials have ends that go in the same direction. Both ends in this case go up. And no matter what kind of polynomial you have, if the coefficient in front of the largest power of x, that's called the leading coefficient, if that's positive, the right end goes up. If you have one where the, let's say we have y equals minus 2x cubed plus 1, if the coefficient in front of the largest power of x is negative, the right end goes down. So you can always tell whether the right end goes up or down by looking at the coefficient in front of the largest power of x. Here it's 1, here it's 1, all these go up to the right. But if it's negative, it goes down to the right. Okay, I have 1 minute left. I want to talk a little bit about scheduling. We are practically finished with our review. We have about maybe 10 minutes of material left. We will easily finish that next class. Then we have a review test. I think I'm going to schedule the review test on Monday, not during class. So basically Monday, you'll have homework and also the review test. I will tell you how to submit the review test. I'll be sharing a Google Drive with each of you, and you'll just put the review test on the Google Drive. So about 10 minutes on Friday will be still review. Then we will start limits. In other words, we will start calculus proper, and that's what we will be doing for the rest of the semester. Are there any questions?
So it would be like given to us after class, not during?
It won't be during class, right? Because we only have 13 weeks this semester instead of 14 weeks this semester. Your midterms are not going to be in class this semester. Midterms will be outside of class. And same with the review test. Any other questions? Okay. See you all Friday.